Here's a question, just totally out of nowhere. Let's consider two statements about a hotel. The first statement is the most expensive room in the hotel is $639 per night. The second statement is every room in the hotel is less than or equal to $639 per night. Which of these two statements is a stronger statement about the hotel? That is, which one is more informative? Think about that. Okay, so the correct answer is A. It is more informative to say the most expensive room's exact price. And here's why, okay? So let's consider that wrong answer. Well, okay, there's two places in the world that I've chosen here where all rooms are less than or equal to $639 a night. There's the Ritz-Carlton Lake Tahoe, and there's the Comanche Motel, which is a really nice place to stay in Fort Stockton, Texas. I've given a link here if you ever want to go there, sing some Merle Haggard karaoke with the owners, whatever you want to do. These two places are quite different. One is an image of luxury and one's a motel in the middle of the desert. But it is true that for both of them, all rooms are less than or equal to $639 a night. By contrast, only the Ritz-Carlton Lake Tahoe, which is not paying me to do this video, has the property that the most expensive room in that hotel is $639 a night. So this statement narrows down the field of possible hotels more. Okay. So what does that have to do with 61B? Well, here's a similar question, which I'd like you to consider. Suppose we have a function and two possible statements about the runtime of that function or a piece of code. The first statement is the worst case runtime is big theta n squared, and the second statement is the runtime is big O of n squared. Which is a more informative statement? All right. Similar to last time, A is the answer, and B, we'll focus on that first. So let's think about all of the functions or pieces of code that might have runtime of big O of n squared. That includes functions like dup4, which have a runtime which is exactly big theta n squared, but it also includes functions that are very fast. So for example, this function that takes an array and it prints out its length. So even if that array is 1 billion items long, this is still going to be very fast, just printing the length. But we can still say that it's big O of n squared, because remember, big O is just a statement about, it's a less than or equal to statement. That's what it does for us, okay? By contrast, saying that the runtime is big theta of n squared in the worst case, that is a much stronger statement because it tells us in the worst case exactly what's going on, okay? So big O is less than or equal to, and theta is equals. So a statement about equality is going to be stronger than a statement about inequality, right? Okay, so I bring this up because it's one of my personal pet peeves. In the real world, people often use big O, where big theta would be a more informative statement. So you'll see people all the time saying things like, hey, merge sort, well, that's a big O of n log n algorithm. And that's true, absolutely true. However, it is not as strong of a statement as saying that merge sort is big theta of n log n. It's kind of like if you were talking about someone's running skills and you say, well, they ran a mile in 3 minutes and 35 seconds, very fast. That is more informative than saying something like they ran a mile in less than 6 minutes. This is an inequality, this is an equality, this tells me more. Okay? Now, despite this lower precision about what a big O statement tells you, it is used way more in conversation. So if you're at a job interview or talking casually to strangers about algorithms, just big O is probably the thing that people are going to use. And it's technically true what they're saying. It's just not as strong a statement. But one thing I do want to note is it does not mean worst case. And it's very often abused to mean worst case. And we could see that very obviously here. The worst case for print length is not going to take quadratic time. Yet occasionally people will use big O to mean worst case. So just be careful, okay? It's not what it means. Now, what good is big O, right? We know what it is, so why would we use it if big theta is more precise? Well, one reason, and the most important reason I think, is it allows us to make simple blanket statements. So if I'm talking casually about algorithms, I can just say binary search is big O of log n, instead of having to say binary search is big theta log n in the worst case, right? Like that's just more stuff you have to say, and I lose a little bit of information for exactly this reason, for the analogy with running, but it's not such a big deal, okay? So it's usually okay. Another reason that is a little less common is sometimes we don't know the exact runtime, so we use big O to give an upper bound. And an example of this would be, imagine an algorithm that finds the shortest path to fly all over the world, minimizing the time you need to get everywhere. The best known algorithm is big O of 2 to the n under certain assumptions I won't state here. And there might be a faster algorithm to compute that best route, but nobody knows that route yet. Or sorry, nobody knows that algorithm yet. Okay, so the algorithm, it takes runtime to compute the route 2 to the n, where n is the number of cities in the world. Okay, and maybe someday someone finds a better algorithm, but for now we'll just say that it's big O of 2 to the n. Okay. And lastly, it is easier to write proofs for big O than big theta. So an example with merge sort, you may remember our just slightly dicey proof last time, where we assumed that the length of the array was a power of n, or power of 2. To fix the fact that that's not always true, we can, instead of proving a big theta runtime, prove a big O runtime. So for example, if I have an array of size 56 or something like that, I would round up to 64. And because 64 is a power of 2, our proof all works out nicely. And so the runtime for merge sort for a non-power of 2 is going to be big O of the next power of 2. And this is getting a little technical, so I'll just say it's a little beyond the scope of the course. But if you want, there's some extra problems in the study guide where you can do this. Okay? So that's it for big O. And so next we'll tackle one other piece of notation, but I want to just point out, it's just my personal pet peeve. You're not going to get thrown out on the streets if you slightly abuse big O versus big theta, but wanted to set the story straight here, just so we could be good citizens of the world.